I'm Dr. Steve Nissen, and I'm here with a friend and colleague, Dr. Stan Hazen, who is the section head for co-section head for the section of preventive cardiology, and both a basic and a clinical researcher. We're going to talk today about the gut microbiome. Stan, you've spent a lot of time working on the gut microbiome. I think we've learned that it's not just kind of a passive participant, but it's actually a very active area. Could you give us a little sort of background of where you've come and where we're going here?
So this all began, we were looking for chemical signatures in blood that predicted future development of disease, like heart attack, stroke, and death. And what we found were that many of the compounds in the blood that actually were strikingly associated with future risk for disease could only be made by bacteria.
Why could they only be made by bacteria?
Well, because some of the compounds are literally things that you don't find necessarily in nature other than made by
in bacteria.
And so it turns out that one of the major ones is we now see is a compound called TMAO, and it is a blood test that is available and predicts future risk of heart disease. And it basically is made by the bacteria in the intestine, and it's derived from nutrients that are abundant in a Western diet. So when we eat foods that are high in cholesterol and fat, they're also high in some of these nutrients that give rise to making TMAO. And this helps, we think, in large part account for the elevated risk for heart disease that is seen with a Western diet that's high in red meat.
Yeah.
So red meat has something called carnitine in it, which is a precursor for making TMAO, and we have seen that a high diet rich in red meat will significantly elevate TMAO levels. And some of this is new work that's come out in the past year with diet intervention studies where we had diets that had all of the protein coming from either red meat, white meat, or vegetarian source, and saw, this is in over 100 subjects, could show that the TMAO level would go up anywhere from 3 to 10-fold in subjects after a month of being on a red meat-rich diet. And then it would come back down after switching to a white meat or a vegetarian form of diet.
Now, you're only talking about beef. What about pork and what about what about non-white meat chicken, that sort of thing?
So actually, veal and lamb, for example, have very high levels of carnitine. So, and even pork has higher level of carnitine than a white meat like poultry. So, the poultry, whether it's white meat or dark meat, has lower level of carnitine, and therefore we think is more heart healthy than, unfortunately, than pork.
How does TMAO
or beef.
How does TMAO cause heart disease?
Well, it does several different things. One thing that has been shown is that it actually changes how sensitive your body is to depositing cholesterol in tissue. So even though it doesn't change the cholesterol level in the circulation, it will very strikingly change tissue cholesterol level. And so think of it, I always give the analogy of the rheostat on a light switch. And cholesterol is the electricity to turn on the light. But you can have the rheostat turned up high or low, and how bright the light is the same as how much atherosclerosis or hardening of the arteries you will get, how much cholesterol will deposit in the artery wall. With a high TMAO, you get a very high amount of cholesterol deposited in the tissue. But even bigger than the atherosclerotic plaque component, I think the bigger effect of TMAO is it fundamentally alters platelet function. So it makes your platelets have a trigger twitchy. They're much more prone
to stick.
They tend to be clumped more and to be more active, and so a submaximal level of a trigger, a stimulus, will result in a much more robust clotting event. And that's why we see the bigger association between TMAO level and clotting risk, like heart attack and stroke and thrombotic events. And some new work which has come out in the past year has shown that as we're trying to develop drugs that block this pathway, they will fundamentally alter thrombosis potential in vivo in animal models. But the advantage is while it lowers TMAO and will lower clotting risk, it does not cause bleeding as a complication because you only take the rheostat on the platelet function back to normal. So you don't have less than normal platelet function.
Do we know what bacteria do this?
We do. It turns out that it's not a single bacteria, but it's a subset of bacteria that are found across multiple different forms of bacteria. So we used to think of bacterially derived diseases as either infections or with the era of H. pylori and ulcers, we think of a single pathogenic microbe causing a disease. But many of the gut microbial disease processes are a common underlying biochemical pathway that a subset of the microbes have. So we think somewhere around 5% of the microbes in the colon have the capacity to do this activity. And therefore, one of the approaches we've been doing is not to try to kill the bacteria, but to give a drug that blocks the bacteria from doing this pathway. So I think our future will have drugs that are a bacterial enzyme inhibitor, much in the same way a statin is a Homo sapien enzyme inhibitor to block cholesterol. We will have drugs that block pathways in the bacteria but are non-lethal to the bacteria. And that
it could potentially not be even absorbed into the bloodstream.
And in fact, that is the approach that we've been doing for the drugs that are being developed. The most current high-potency inhibitors that have worked in animal models, they have not yet been taken into humans. But they are very poorly absorbed, and over 99% of the drug stays in the intestine and targets the bacteria. You have a very brief, very minimal exposure in the bloodstream, but then it dissipates very fast. And because it stays in the GI compartment, we're seeing, at least in animal models, that we can give a dose and inhibit the bacterial enzyme pathway for several days in a row. You have no measurable systemic exposure, and yet you inhibit in the host any demonstrable TMAO being present because the gut microbiome isn't producing the metabolite, the precursor.
And how much can you reduce TMAO with this strategy?
Literally 98%.
You can literally reduce it almost to zero.
Almost to zero, yeah.
Yeah.
So at least in the animal models, we have not done any inhibitor studies in humans yet. That is our next stage, and we and others are racing for that goal. We think that this is going to be one of the first targets where the gut microbiome will be treated with drugs, impacting diseases like heart disease and chronic kidney disease.
What happens with vegetarians?
So with vegetarians, they have lower level of TMAO, but they're not without risk. The reason why is our TMAO comes from two main sources. There's the carnitine source, which is found in red meat.
Yes.
But then there's also phosphatidylcholine or lecithin or choline, which is the second source. And whether you're an omnivore or a vegetarian or vegan, your bile is a very high abundance phosphatidylcholine. It's part of how we digest fats and lipids. We dump cholesterol and phosphatidylcholine into our intestine, and it helps digest the food, and then it gets reabsorbed. But a chunk of that makes it past the small bowel to the colon, and we feed our bacteria with this as well. And so vegetarian and vegans can have a very high level of TMAO because of the phosphatidylcholine or choline source. It's a different set of bacteria, but it's kind of the same type of reaction, and that's actually the pathway where our drug development efforts have focused, because we think that will be important for everybody, omnivore and vegan alike. And the omnivore cutting back on red meat ingestion will literally eliminate carnitine as a source. The only way you get carnitine in the intestine is by ingesting it, and that comes either from red meat or many energy drinks and supplements can have carnitine as an additive, but it really is not necessary. Our body makes all the carnitine that we need.
Now, the one diet that everybody, it's been shown to reduce heart disease is the Mediterranean diet.
Yes.
So do you have any thoughts on what's going on there mechanistically?
So there's many different ways I think that a Mediterranean, how any diet can impact heart disease. But with respect to the gut microbiome and the TMAO pathway, we and others have been able to show that a Mediterranean diet will lower TMAO levels. A cornerstone of the Mediterranean diet is reduction or elimination of red meat as the protein source. So the Predimed trial, for example, had no red meat as one of the instructions.
Lots of olive oil, though.
And that's the second aspect. The earliest inhibitors that we developed for this pathway was a compound that has since been found to be present in extra virgin olive oil.
How about that?
And grapeseed oil. And it's interestingly, it's a small alcohol like ethanol, just a little bigger. And if you cook the olive oil, you cook off the compound. So whereas we in America will often, fry with oils, including our extra virgin olive oil, in Mediterranean countries they just drizzle it on top and don't cook with it as much. And we think many of the health benefits of extra virgin olive oil will be lost if you actually heat it too much.
But you can put it on your salad, and it's not been cooked.
That's correct, or on top of soup, or on top of bread, or wherever, however you use it.
Yeah.
So we actually have ongoing clinical research studies where we're looking at the impact of a Mediterranean diet rich in extra virgin olive oil and what its impact on the TMAO pathway is. And so while we haven't finished that study yet, there is data out there already supporting the concept that a Mediterranean diet, and the more compliant with a Mediterranean diet you are, the lower you can lower TMAO level.
So when do you think that these inhibitors of these pathways are going to be ready for first-in-man studies?
Oh, I think they'll be ready for first-in-man studies in 2020. Now, whether or not they become commercially available is another study.
Sure.
Is another point. So we believe that they will be, first-in-man tested in the coming year.
Yep. Are there any other products of the gut bacteria that you think are important in the genesis of heart disease?
I think there are a few. So now whether or not we can leverage this information and improve our health is a different question. It turns out that short-chain fatty acids are the end stage products or waste products of gut bacteria, and they have been shown to actually impact some of them, not only energy metabolism, but also diabetes risk and lipid levels in animal models. And so there are ongoing human supplement studies looking at different short-chain fatty acids, whether it be acetate or propionate or butyrate. There are also many different groups that are trying to come up with a probiotic that might increase the level of these things. I think that's a much harder target to do because the microbial community in the gut is so large and so complex. When we give a microbe in the form of a probiotic, how it ultimately terraforms the community and shifts the composition is very hard to predict. And it just literally takes trial and error testing and studies to figure out which one. But I would say those are some of the main ones. There are others that are, all I can say is stay tuned, that there are new pathways, just like TMAO, that we think are linked to not only the disease development, but responses to therapeutics that will be coming out.
Well, thank you very much, Dr. Hazen, for bringing us up to speed on this amazing work. And, this has happened very quickly. Understanding the gut microbiome and its role in heart disease. Stay tuned. There's going to be a lot more to come. And thank you for watching. I'm Steve Nissen, here with Dr. Stan Hazen, co-section head for preventive cardiology at the Cleveland Clinic.
Thank you very much.